Okay, welcome everybody to this behind the scenes presentation on the EASY project. So we wanted to give a more in-depth technical view on what we're doing in the EASY project, how we're doing it currently, and what we're working on right now, what we want to work on in the near future. So first of all, thanks a lot to Bob and Terje for helping out with putting together the presentation. We will share the slides afterwards. The meeting is being recorded and we will share that shortly after the meeting as well. There's one link here, which I'll also share in the chat. So this is a collaborative document where you can add notes and add questions. So it'll probably require you to log in first. So you can use your Twitter or your GitHub account to log into HackMD, and then you should be able to add some notes there. So feel free to do that if you want to. What we'll cover today is a very high-level overview of the EASY project itself, similar to what we've done in previous presentations, but we won't spend a lot of time on that. So this is not an introduction to what EASY is about or how you can use it. It's really going behind the scenes and looking into how we did things, what we want to work on it next, the plans we have for the project, and so on. We'll show some of the tools we use, some of the workflow, so how we have put things together up until now, what we're working on right now. We'll give an overview of the current status of the different layers, so things that work, things that don't work, things that we're happy with, that we're not happy with, and then goals and plans going forward. And all of this is sort of mixed together, so it's not bullet by bullet, but you'll see things popping up throughout the whole presentation. This is just very briefly for maybe people who are not aware yet. I hope everybody is, but what the EASY project is about. It's the European environment for scientific software installations. We still have the idea to change the European to something else, to make it a bit more open for collaboration to people outside of Europe. It's a collaboration between different European partners and even people outside of Europe already. And what we want to do is build a common scientific software stack for HPC clusters, but also cloud, workstations, and so on. And it's a grassroots project, so we're actually working on this already, sort of on the side, but it's currently not a funded project, so there's no dedicated manpower for this. The collaboration with the HPC and NRW consortium sort of changes that, because it seems like some people will be able to spend some of their time in contributing to the project. So that's definitely slowly changing as well. The goals and the scope of the project. So we want to set up a shared repository of scientific software installations that are properly optimized for the hardware on which they will be run. So not something like RPMs, which are very generic, but something that's really optimized for the CPUs on which they run. And by working together on this, we hope to help out each other and avoid lots of duplicate work that's still happening across HPC sites. For the end user, it's a uniform way of giving them software. So whether they're logged into an HPC system in Germany or one in France or one in the Netherlands, or they're using AWS or Azure, they basically get the same software installations. It looks the same. They can use it in the same way. So it's a very uniform experience that we're trying to provide. And the idea is that it works on any Linux distribution, macOS included eventually, and also any system architecture. So any CPUs, eventually any GPUs that you have, we hope to get it working there. So this goes from laptops to HPC clusters, cloud, even simple toy computers like Raspberry Pis and so on. We want to support a wide range of CPUs, properly use the interconnects like InfiniBand or Omnipath, use the GPUs for where it makes sense for software and so on. So the focus is, I would say, primarily on performance. That's one of the driving goals of the project. We want to make sure we try to automate the deployment of the software, including testing. And of course, we want to work together to make this happen. The partners that are currently involved already. So on the left, there's like the founding partners. which is Dutch universities together with the University of Cambridge and Dell Technologies. And they invited me in February of last year to join a meeting. The project didn't exist back then, but the project eventually grew out of that meeting, I would say, where we agreed that we wanted to collaborate on this idea, and then we started forming the name and the GitHub repositories and so on. Then gradually more and more interest came from the HPC community. Companies like HPC Now or big HPC sites like CSCS and Jülich started attending meetings and even contributing. And also cloud providers like Azure and AWS have had significant interest in the project and are even either already sponsoring the project like AWS is. In some sense, Azure is as well, but they're working on more structural sponsoring as well. So that's hopefully coming up. And yeah, universities like Oslo or the HPC NRW consortium have at least expressed interest and or already contributed as well. So from a very high level, the EASY project is built out of different layers. So we're including the host operating system, so your Linux distribution or your Mac OS that you have in your system as a sort of base, but we try to use as less as possible, or as we can. So things like GPU drivers, network drivers for InfiniBand, or the Slurm scheduler or research manager, we still use those things from the OS, but everything else we intend to provide ourselves. And this is what the layered stack here is about. So the file system layer, which is the bottom layer of what we provide, just takes care of distributing the software that we provide. So you can access it from anywhere in the world. It easily goes through firewalls, so even on fenced off networks or even clusters where the worker nodes cannot get access to the internet, you can still get it to work. The compatibility layer, which is our middle layer, is how we shield or isolate ourselves from the host operating system. So here we provide everything that we need to install software with. This includes things like glibc, some important libraries and things like that, but it doesn't include a Linux kernel or GPU drivers or things like that. And then the software layer on top is where we actually provide the scientific applications and all their dependencies. So the idea of this layered stack is not new at all. It's heavily inspired by what Compute Canada has done in their software stack. So if you look at what they are doing, and they've made presentations about this, written papers about this, it's very, very similar. There are some small differences in terms of how we do things. There's certainly differences in terms of the scope of what we're doing. So it's not tied to only Canadian HPC sites. We're also pulling it open to other CPU architectures like ARM and Power, which they are not doing. So it's a bit more ambitious than what they did. But we're confident that we can do what we have in mind, since Compute Canada sort of already
Seems like we've lost Kenneth, so I'll try to take over.
You're muted right now, Kenneth.
Yeah, I'm back actually. Zoom just disappeared for me for a while. Okay. Let's hope it doesn't happen again. It still seems to be recording for me. That's interesting. Let's see how that works out. Let me make sure I'm properly set up. So the screen share is back.
Yes.
Yes.
Yes. Okay.
Yes.
Okay, I'll just continue. So yeah, we're confident that we can do what we want to do, since Compute Canada has shown that it works. Then looking into these different layers a bit more. So what are we using to build these layers? So the colors here match with the previous slide. So the bottom layer here is the file system layer, for which we use cvm-fs or cernvm-fs, which is a software distribution mechanism service. So this project was created at CERN for the Large Hadron Collider project a long time ago, I think even over 10 years ago. Since they had to distribute their software all across the world, they wanted to do this in an efficient way. One important detail here is that the software that's being distributed here is actual software installations, not packages. So it's not things like RPMs, which you then have to install. It's the actual installations themselves, so the individual files that make the installation. And that's an important detail, and I hope that will become clear once we show what we have currently. It scales really well. It's being used on repositories, so yeah, collections of these software installations that have hundreds of thousands of files that are used by thousands or even tens of thousands of clients across the world. So that shouldn't be a big concern. One important other detail is that it's read-only, so whoever accesses the file system only has read permissions, not write permissions, which is also, that's good enough for a software distribution service where people are mainly interested in using the software. Of course, it's writable for the people who maintain the software stack. And then the way it works internally, it's basically using web servers, so it's only doing HTTP traffic between client and server. So it's very easy to get through firewalls and things like this. And you can use proxies, you can use caching, which is all pretty standard in web servers. The middle layer, the compatibility layer, is where we use Gentoo, and more specifically a sub-project of Gentoo, which is called Gentoo Prefix, where you install core libraries like glibc and things like this in a particular installation prefix, so not in the standard /root file system, but in a directory that you choose yourself. So this doesn't work with traditional pre-built packages like RPMs, but it works with Gentoo because Gentoo installs everything from source, so it's able to just relocate things at installation time. Gentoo and Gentoo Prefix have support for x86 64-bit, for ARM 64-bit, for Power. I don't know if they're already working on more exotic things like RISC-V or something, but I would imagine that's something they wouldn't mind working on. And it supports both Linux and Mac OS. So you can install a Gentoo Prefix Linux distribution in a Mac OS host. And of course, it works on Linux as well. So it basically provides everything we need to achieve the goals that we have. And both cernvm-fs and Gentoo are also used by Compute Canada. Then on top, the software layer, we use 3 different projects. The EasyBuild project is one I have been very involved in the last 10 years. So EasyBuild is an installation tool for scientific software. Whenever it can, it builds the scientific software from source, and it also optimizes for the build host. So if you're using EasyBuild on an Intel Haswell system, you will get installations that are optimized for Intel Haswell. It supports well over 2,000 different software libraries, applications, and tools, so without versions. And that's not taking into account things like Python packages or R libraries. They're not included in this count, so it already supports a wide range of things. Let's jump to the right first. The LMOD tool is an environment modules tool. So where you expose software installations through modules, and users do things like module avail to check which installations are available, or use module load to change their environment to use that software. So that's a pretty well-known concept in the HPC community. LMOD uses Lua or is implemented in Lua internally. It supports module files that are written in Lua or Tcl, so you can do both. And yeah, for the end user, it's a fairly intuitive access to the provided installations. You can have multiple software versions side by side, and each of them comes with a different module file, and people can swap between them and do all kinds of fun stuff to set up their environment. Both EasyBuild and LMOD are also used by Compute Canada. The middle one, ArchPack, is a fairly new project. It was only started or at least pulled out of another project in January of last year. So it's a small, relatively small Python library that detects what kind of CPU you have. So you can ask Archspec, on this system, do I have a Haswell or a Skylake CPU, or is it AMD Rome, or is it some ARM CPU, something like that. So it knows how to detect that. It basically checks proc CPU info on Linux. It works on Mac OS as well. So that's the basic thing it can do. What it can also do is check which CPUs are compatible with each other. So if you're on, let's say, a Broadwell system, it can tell you that binaries built for Haswell will work, but binaries built for Skylake will not work. So it knows what is compatible with what, and it can give you the closest match to your host from a range of options. Archspec is something we use that Compute Canada doesn't use. So that's already one small difference compared to what Compute Canada does. And then Reframe is sort of separate. It's not actually part of any of the layers, but it's the tool we plan to use for testing the software stack that we provide, both for the compatibility layer and the software layer. So Reframe is also a Python tool. The tests are implemented as Python classes. It's not really scripts, but yeah, you have to implement things in a certain way in Reframe. And we plan to use this to both verify the correctness of the installation. So do they work? Do they produce the correct answers? And so on, and also to evaluate performance. So Reframe has very good support for checking the performance of a test that you run. For example, you can tell it this test has to finish between 5 and 7 seconds, and if it's in that range, it's okay. If it's outside of that range, either faster or slower, then it flags the run and says something's wrong here. This was too fast, so maybe it didn't do what it was supposed to do, or it's too slow. Something was affecting the installation, and it makes it slower than expected. Then other tools we use more on the side or underneath the covers, maybe, so they're not as visible, but we use Ansible. So Ansible is a tool for automation and configuration management. So while Bob is fixing my typos, so with Ansible, you use some kind of scripts, which are not really scripts. They're implemented in YAML, and they're called playbooks. And you can run an Ansible playbook to make sure the configuration of something is correct. So yeah, it's a pretty well-known tool, I think. We use it currently for deploying both the file system and the compatibility layer. So we have playbooks to make sure that everything is properly configured, the necessary packages are installed, the necessary configuration files are created, and so on. So that has worked out pretty well. We also use Singularity, so the container runtime system for HPC, which is really intended for HPC. It both has its own container image format, or it consumes Docker containers in the pretty standard format. We use Singularity to have full control over the build environment for the compatibility layer and the software layer. So we make sure that we are shielded of the operating system that is installed on whichever servers we use. So when we want to build software from source, we always do it in a container environment, so we know which packages are installed, which operating system we're running in, and so on. So then that enables us to basically use any server as a build server for the EasyBuild project, because we are in full control of what's available and what is visible to the build procedure. In addition to that, we also have a container image that you can run via Singularity to get easy access to the Easy software stack. So as long as you have Singularity available on the system, you can get access to the Easy software without having to install something like cernvm-fs on your host. So if Singularity is already there, you don't need admin privileges to get access to the Easy software. Then Terraform and Cluster in the Cloud are not really used yet currently in the Easy project, but we do have plans for using them. Especially with Terraform, we've played, or Terry has played around a bit already. So Terraform is a tool to create and manage cloud instances. So you can give it some kind of script that says, go to AWS and give me a 2-core Intel Haswell VM in the AWS cloud. And then you can run stuff there to maybe build software or to test something. And afterwards, you can let Terraform tear down the instance again and clean stuff up. So we're hoping to use this to create build nodes on demand in AWS and Azure. Since we're getting some sponsorship from both of these, we actually have quite a lot of resources there that we can use in a way that's useful to the project. And in order to make efficient use of these resources, Terraform will be a good way to make sure we only spin things up as we need them and to tear things down again afterwards once the node has fulfilled its task. Cluster in the cloud is another project that may be useful, especially for testing, maybe also for building or having a collection of build nodes that we can use. It's a command line tool to quickly create a Slurm cluster in a cloud environment where you have control over which nodes are included in the Slurm cluster, how many, how big, what kind of types of worker nodes you include in the Slurm cluster. So it's very easy to set up a heterogeneous Slurm cluster, for example, in AWS. And for example, you spin it up in a matter of minutes, it's there, it's fully provisioned. You can play around with it, you can use it for whatever you want to use it, and afterwards you just kill all the VMs again and the Slurm cluster disappears. So it's again an easy way to use cloud resources and just throw them away once you're done with what you had in mind. So for now, I have played around with this a little bit, it works really well. And I think we can put it to good use in the project. Then back to the layers. So why do we have these layers? I think I already covered this a bit. So we only rely on the operating system of the client for things we cannot or should not provide ourselves. So things like GPU drivers, it's closely related to which GPUs you have. It's closely connected to the Linux kernel that you're running. So there's no point in trying to get that, trying to provide it ourselves. We probably won't be able to. You also need kernel modules and things like this. So you need admin privileges on the clients. And so there's no way that we will get people to install the stuff that we provide whenever we need root permissions. That's just not going to work. For the file system layer, we use cernvm-fs to distribute the software. I think I already explained that well. The compatibility layer levels the ground across client operating systems. So it makes the client OS as irrelevant as possible. So whatever we can provide, things like our own glibc, we do provide via the compatibility layer. We provide our own Python 3 installation, so we know which exact Python 3 version we are using and not a 3.8 or a 3.6 that's provided by the client. And for some of the other tools like curl, it also makes sense to provide them here for a variety of reasons. And then the software layer, provides the software itself. And this is where we properly optimize things for a specific micro architecture, which we do not do in the compatibility layer. So before I hand it over to Bob and maybe take some time for questions, let's take a closer look at the client OS and the CPU architecture. So where do we stand right now? So we only rely on the client OS for Linux kernel, for drivers, for InfiniBand and GPU, file system stuff like GPFS, Slurm scheduler. So if it's there, you can still access it from the client operating system. We don't want to provide things like this ourselves, or we shouldn't in some cases. And the only other thing we rely on heavily from the client OS is either to have cernvm-fs installed in the client OS as a native installation, or if you have Singularity installed, you can get access via the container we provide as well, which certainly works well single node. You can also get it to work multi-node. That's a bit more work, a bit more setup to do, but it can also work. So even if you don't have cernvm-fs installed in your client, you can still use the Easy software stack. Things we do not use from the client OS, as I already mentioned, are lots of libraries like glibc. We provide our own glibc in the compatibility layer. The host compiler is not used at all. Tools like patch and make and sed or whatever other tools we use are all pulled from the compatibility layer, not from the client OS. So there's multiple reasons for this. First of all, we want to shield ourselves from the client OS, and that helps with making sure that whatever we provide in the compatibility layer and also on top of that works no matter which Linux distribution you have or no matter what's installed in there. And it also makes sure we have full control over the version of the compiler, the version of glibc, which may be important in specific cases. What we want to support in terms of compatibility with clients is a wide range of CPU families eventually. For now, we've been focused on x86 and ARM 64-bit. That has worked out pretty well. Power is a work in progress, as Bob will explain a little bit more about that. And in the longer future, we also want to look at RISC-V, which is an upcoming CPU architecture. And with the whole way that things are designed, it's as long as the software is ready for it, we can easily add RISC-V as a supported architecture as well. And for the operating system of the client, any Linux distribution should work or actually already works. And then includes the Windows subsystem for Linux environment, which is basically like a Ubuntu VM running inside of Windows. That also works. So the software we provide in Easy also works in WSL already. Mac OS currently doesn't work yet, but we've made some good progress towards that in the last couple of weeks. And it's something we want to properly support eventually as well. What has been tested, what works really well. So in terms of client OS, we've tested what we have right now on a variety of Linux distributions, certainly including CentOS, but also Ubuntu and Debian. And we're not really aware, I think, of any big issues there. That all seems to work well. Same thing for Windows subsystem in Linux. That seems to be working well. Even graphical installations like ParaView that we provide seem to be working fine. The Mac OS support is work in progress. So I think we got it up to a point where we can install Gentoo prefix, but maybe not fully in the way we want it to. So I don't think it includes glibc yet. Is that the issue, Bob, that we have still there, or is that a fixed issue?
Yeah, as far as I know, it's still not using our glibc yet. So
yeah, so that's one thing we haven't fixed yet. We do know that cernvm-fs works in macOS, so you can install cernvm-fs in macOS and you can get access to the Easy repository, but it won't be of much use there because there's nothing in there that's actually compatible with macOS currently. But at least one of the layers is already covered, and we're working on the compatibility layer. Oh, oops. And CPU architectures, yeah, both x86 and ARM 64-bit work really well. We provide installations in the software layer for Intel Haswell and Skylake, also for AMD Rome. And we have a fallback to generic x86, which is anything that supports SCC2 is good enough to run these installations. And similar for ARM, we have a generic that falls back to a pretty basic ARM instruction set. For example, you can run these on a Raspberry Pi. That works really well. We have specific builds for Graviton 2, so that's the ARM CPUs that are available in Amazon. And also for Thunder X2, I forgot the vendor of this, but this is ARM CPUs that are available in an ARM cluster in the UK, for example. For power, it's not working yet. We're still stuck with some issues with Gentoo prefix. I think also related to glibc, where it's not fully working yet the way we want it to, and we're getting some help from the Gentoo developers on fixing that. And it's not a real top priority right now, but it's certainly a work in progress. And RISC-V, yeah, that's nothing more than an idea right now because we don't have access to hardware, or at least capable hardware yet, that would allow us to get started. I think now is maybe a good time to pause a little bit for questions. So I don't know if anyone has any questions to ask. Something was mentioned in the chat. Ah, okay, it's just Christian. Any questions currently before we continue? Ah, in the hack document.
Yeah, I don't know if you want to answer that one now, but it's about the design decisions of Compute Canada.
Compute Canada made some design decisions that made him not want to use. Okay, that made, yeah. What was that decision, and are we sure that our design does not suffer from such a problem? Okay, that's a good question. So we're very early in the project. Of course, we knew very well that we were looking at what Compute Canada has done. We wanted to do something similar. The first thing we did after the meeting last February was actually reach out to the Compute Canada people and have a discussion with them. Like, we want to do something like you did. Is there a way that we can collaborate on what you currently have already and maybe expand it a bit so it works for other sites as well? Is that an option, or does it make more sense to do our own thing? And after a bit of discussion, both parties actually agreed that it was better to start from scratch and do our own thing. Some of the things they have done in the Compute Canada software stack is in some sense specific to Canada. So they've made some design decisions that maybe we are not happy with. One thing is, for example, hierarchical modules. So that's maybe not a good fit for everybody. Right now, we have a very flat module tree, but we have the idea to actually provide different views on the software stack. So not have one module tree, but multiple ones, which is probably not something Compute Canada would like to get into. I think they're also stuck on LMOD. So they expect you to use LMOD, which is something we want to be a little bit more flexible about. By, for example, providing both Lua module files and Tcl module files. So if you have a Tcl only environment modules installation, you can still use our software stack. One thing we are doing, and they are currently not doing, and I think they're also not interested in it, is supporting things like ARM and Power and eventually maybe RISC-V. So we're a bit more ambitious than they are. So yeah, after discussing with them, I think it was clear that the best way forward for us was to start our own thing. So we are in control. We have the freedom to make design decisions, to maybe make it a bit more ambitious. And also from their side, letting other sides have a say in what they provide and how they provide it, that would have been very difficult to get official approval to make that happen. So that setting up that whole workflow or the policies related to that, it didn't really seem that they were open for looking into that, or it would be a problem to make that possible. So yeah, there's various aspects that made us do our own thing and look what they did, try to learn from the mistakes they have made. We're definitely in close touch with the Compute Canada developers. So whenever we want to discuss something with them, they're in the Easy Slack. They're happy to answer our questions and happy to work with us. If there's something they have figured out and we cannot figure out, or if we have any questions related to what they did, they're definitely open for answering them.
And most of their code is also on GitHub, or if not, they're often willing to give it to us. So yeah, we can basically take anything that we need from them. So both help and code and support.
You can usually check what they have done and either see if we're happy with that or if we want to change something. And in some places we've literally done that, taken what they have and just improve it a bit or change it a bit with something we are happy with. Would it make sense to embed the Gentoo prefix inside Singularity? Not really. So the reason we have the file system layer is to easily distribute the software stack. So the container image we provide, the Singularity image we provide, or actually the Docker container we provide that you can run through Singularity to get access as a client to the software stack, only really has cernvm-fs in the container image. And that's used to access the EasyBuild repository, which has both the compatibility layer and the software layer. I guess the question is maybe, can we avoid having to use cvm-fs? If you use the container image we provide, you don't need cvm-fs at all. All you need is Docker or Singularity to get access. So yeah, I'm not really sure what the question is, why you would want to do that. Actually, you could have Gentoo prefix inside of a Singularity container, but it doesn't make a lot of sense, because if you're using a container image, you're already in full control of the operating system. So you don't really need Gentoo prefix anymore if you want to install software in there. So I don't know if that's a good answer to the question.
Maybe one possible use case. I know that Christian might also be interested in that, since he also asked that before. You could, in principle, make a standalone container which includes a Gentoo prefix installation, and then, for instance, add one or a set of applications from our software layer into that container as well. And then you don't need cvm-fs at all anymore. So then you basically wrap everything into a container which you can ship to whatever system you want to run it on. But already said more or less, you can of course also just build that container yourself without Gentoo prefix. So then base it on whatever operating system you want to use.
Yeah, there could be a use case where you just rsync what you need from the EasyBuild repository, shove it into a container image, and just happily continue with that. That would work. But then again, the container image will be specific to a particular CPU architecture like Haswell or something, and it wouldn't run on ARM, or it wouldn't properly run with good performance on Skylake. So you're going backwards rather than forwards. At least to me. I'm sure Christian disagrees with me. Okay, so maybe Bob, now's the time to switch.
Yeah, I'll share my screen. All right. So I will tell you something more about the file system layer and the compatibility layer of the Easy project. So first, the file system layer, as Kenneth already mentioned, it's based on cernvm-fs. And I just want to quickly show you how you have to build up the cvm-fs infrastructure and how it looks like. So basically in cvm-fs, you have several layers of the host, which contains the actual story, and layers around it with replicas and also caches to make things reliable and scalable. So the thing in the middle here, that's called the stratum 0. You can have only one stratum 0. That's basically the source where you add all your software. So that's where you set up the repository, add new software, and then you basically distribute that to different servers. Often you can also not connect directly to a stratum 0 from a client. It is possible. So if you don't have any limitations like firewalls in place, that's perfectly possible, since the stratum 0 is also just a HTTP server, which serves all the contents of the repository. But usually, because this is your most important server in the whole network, you want to shield that off from other, so that only the administrators can connect to this system, and only the stratum 1 servers can connect to the stratum 0. So the stratum 1 servers, that's basically this ring around the stratum 0. Those are basically mirrors or replica servers, which just take a full copy of the repositories that you have stored on the stratum 0. You can, for instance, do that with a cron job, which will just every 10 minutes or so synchronize the repositories, so that those get all the changes from the stratum 0. That's a read only on the stratum 1, so you cannot ingest new software on the stratum 1. And often you have multiple of these stratum 1 servers. So depending on the size of the project and also on the geographical distribution, you might want to add, for instance, one stratum 1 server per country or per continent, or depending on the number of users, of course. So there's also an API that basically detects where a client connects from, and then it can automatically connect you to the geographically closest Stratum 1 server. So that's the Geo API. So if I connect to cernvm-fs from a machine in the Netherlands, then it will basically find all the Stratum 1 servers in the project, and it will do a query which will tell the client where all these Stratum 1 servers are located, and it will basically forward you to the right server, which is the closest one. Just like the Stratum 0, also the Stratum basically just Apache web servers, but the Stratum 1s also have a Squid proxy in them, so that's the front end towards your repository over here, which will just reduce the load on the Stratum 1 servers and cache some kind of queries, which are often done. In principle, clients can connect to Stratum 1 servers. So as I just mentioned, Stratum 0s should be shielded off from direct access to clients, but it's perfectly fine to let clients connect directly to a Stratum 1 server. So how does that work? This is the proxy that I mentioned. So basically every Stratum 0 has a proxy on the same machine. So it's based on Squid, which is used for load balancing and caching. And then the client, so a client can either be a user working on its own workstation. It can also be a HPC cluster. It can be a cloud VM or a cluster in the cloud. Doesn't really matter. And then in principle, this client can, for instance, directly to this Stratum 1 server. So it basically goes through the Squid proxy of the Stratum 1 server here. And then it can just pull in whatever that user needs. So it doesn't pull in the full repository machine. It's just if I want to run, let's say, TensorFlow from our repository, it will pull in whatever file I access from the TensorFlow installation. So basically, while the program is going to run, it will detect, okay, I need this file, so let's pull it in from the Stratum 1 server. Now you can imagine that if an entire HPC cluster with hundreds or thousands of machines are all going to connect to that Stratum 1, the load will become quite high on that server. So to add extra layers of caches, you can add your own proxy servers in between, which will act as another layer of cache. So that means that whatever, again, the TensorFlow library, for instance, it will first go to the local cache over here. So that should be a machine which is very close to your cluster, preferably in the same network. So it will ask the local cache, do you have this file for me? If not, the local cache will connect to the Stratum 1, so the closest Stratum 1 server. Will pull in that file, store it locally in this cache, and then the actual compute node in the cluster will take that file from the cache and also store it locally on its own local disk, assuming it has a local disk. So that's the other layer of cache that you have. So then the next run on that particular machine will first again check, do I have this file on my local disk in the cache? If not, go to the cache over here, where it should then be available, and then it will pull it in again. So that means that basically any machine, so any kind of repository, but it won't store the full repository. It will only store whatever file is being accessed. You can also control the size of your cache on that local machine. So if you just have a small disk, you can define that your quota for the local cache should be, for instance, a few gigabytes. But of course, the larger your cache will be, the better everything will perform. And if you have a small cache, then it makes even more sense to have an additional machine over here which acts as a local cache. You can also have more than one here, so you can have an HPC cluster use, for instance, 2, 3, 4, or whatever number of local caches. And more than one is often recommended. So if that one goes down, that you always have another one. And also the load will then be balanced between those different caches that you have. So that's in short how cernvm-fs works. So right now we have, as a test setup, as I will show later, we have one Stratum 0 server running here in Groningen. And we have 2 Stratum 1 servers, one in Groningen, one in Oslo. And then basically anyone, so the Stratum 1 servers are open to anyone. So basically anyone in the EasyBuild project and to use our pilot repository can connect to either one of those Stratum 1 servers or finish cache with you yourself. So something more about the file system layer, the current setup that we have. So as I just mentioned, we already have a Stratum 0 server and 2 Stratum 1 servers. I also added a local proxy to play around with on our HPC cluster in Groningen. As you can see from the specifications, you don't really need a lot of resources. So our Stratum 0 is very low in terms of resources, so just a dual core machine with a bit of memory. Also the cernvm-fs says that you don't need a lot of resources, especially on the Stratum 0, which will not be used a lot. The only thing that you do need, of course, is quite a lot of disk space, depending on how much software you're going to store in the repository. And the Stratum 1 and the proxies, of course, that depends on how many users or clients you will have in the end. But at the moment, those are not very, they don't have a lot of resources at the moment either. But that's for now more than enough. So we haven't run into weird issues yet. And of course, when we go into production, we do need a lot more Stratum 1 servers and proxies. Also good to mention, don't think I've mentioned before yet, what cernvm-fs also does is it won't ship the whole files uncompressed to clients. So it does a compression and it also does deduplication. So that means if you have multiple installations sharing the same files, for instance, the same text files or whatever, they will be deduplicated and compressed, which means that even if you're going to store lots of software, the actual disk space that you need is still quite limited. So at the moment, we have quite a lot of stuff already in our repository, but the actual disk usage is like 60 gigabytes at the moment. So that's not that much. And I think even Compute Canada says, where they have a lot of software already in the repository, that 1 terabyte should be enough for the entire repository. That should fit easily. So a while ago, also Axel at the University of Oslo set up a Stratum 1 server, as you can see, more or less with the same specs, same amount of disk space. If you want to try this yourself, you're of course welcome to do so. That should be rather straightforward. I will show you on the next slide how that looks, what kind of playbook you will need to run. And then we just have to add it to the configuration of our repositories. So for each layer in our project, we basically have a kind of primary contact. So for the file system layer, that's me. So if you have questions, feel free to ask me, or you can ask in the dedicated Slack channel that we have for the file system layer. So for the file system layer, we use Ansible playbooks. So I can show you how that looks like at the moment. Let's switch this tab on GitHub. So this is the file system layer repository in GitHub. I can zoom in a little bit, if that works. So as you can see, there are in the main, in the root folder, there are multiple. Zoom out a little bit. So there are multiple playbooks here in the root folder of the repository. For instance, one to set up a Stratum 0, one to set up a Stratum 1, one to set up a local proxy, one to set up one or a bunch of clients. So suppose you want to run a Stratum 1. Basically, you can just run this playbook, which makes use of an Ansible role, which is not developed by us, by Proxy project. So that's going to be run here. And we have an inventory that's basically a list of machines and a list of settings that we use for all these playbooks. So that's quite detailed, so I won't go through that right now. But basically what you will have to do, you have to provide some kind of name or IP address of the machine that you're going to use as your Stratum 1. You have to set up a few variables, and then you can just run the playbook, which will deploy all the components that you will need on your Stratum 1 server, and then it will just set it up for you. Well, similarly, there's one for Stratum 0, but that basically only has to be done once because you can have only one Stratum 0. Also for the client, if you want to use Ansible for the client, you can make use of this rule, which is fairly simple. It will just take from our configuration file what the name of the repositories are, what the IP addresses or host names from our Stratum 1 servers are, and it will configure your clients. And basically all the machines that you put in a section called cvm-fs clients in your configuration file will then be set up automatically for you. So it will install the client, install the configuration files that you need, and then just start the cvm-fs or mount the cvm-fs repository. So I think that's the quick overview of what I want to show here. Can quickly open the main configuration file to give a very quick impression how that looks like. So this is basically what you don't have to change, but this contains, for instance, public keys to our repositories, which will be used by the playbooks. It contains the URLs to our Stratum 1 servers. So here you can see that we have one for the RUG, which is the University of Groningen, and one for the server in Oslo. So if you want to add your own Stratum 1 server, you can first just configure it, and then you can make a pull request, which basically adds the URL to your server here as well. And then clients can just start using them. And just another bunch of settings for our repository. So I won't go through that right now. So how does that work in practice? If you want to use our repository from a client side, basically what you will have to do is install the cvm-fs client, which you can just take from the cvm-fs website from the downloads page. And then you have to configure our repository, which you can do by installing a package that we provide. So that's available here on the release page of our repository, which I can quickly show. Go here, go to releases. So every time we make a version release of the whole repository, we have a GitHub action that will automatically build packages. So at the moment we provide an RPM package, a dep package for Debian and Ubuntu, and a macOS package file. Also the source code itself, it's not really useful. But basically you can just take one of those packages and use it to configure your client. You also need a machine-specific configuration file, so that's not included in the package specific to your machine. And that holds, for instance, configuration items like how large your cache should be for cvm-fs, to which machine you want to connect, or either directly to one of our Stratum 1 servers, or if you have your own cache in between, then you can also add that to your configuration file. So everything you can find here. Also, there are lots of GitHub actions configured on our repository, which basically will run every time someone pushes new code to the repository. What it will do, for instance, if we make a change to one of our playbooks, then these GitHub actions will run, and it will try to run all the playbooks on different kind of operating systems. So it will basically run a bunch of Docker containers, one for Ubuntu, one for CentOS, one for CentOS 7, one for CentOS 8, and it will just run all those playbooks and see if they still work correctly, so that we can be quite sure that we don't make stupid errors in new commits. There's also quite a lot of documentation now in the README file of the repository. So down here you will see instructions for running all these different playbooks for the different components, so all the kind of configurations that you have to do yourself, and then sections for Stratum 0, Stratum 1, the local proxies, the clients. So basically everything you can find here, but we want to move that soon to the documentation page because it's getting quite extended now, and well, this information should fit better in the documentation page than in a README file, especially the client instructions. Something more about the configuration of clients. So what we use is a so-called cvm-fs configuration repository, which is a repository of itself, and that basically only holds configuration files for clients. So I can show you how that works. So usually you put all your cvm-fs configuration on your host machine in etc cvm-fs. And then you have to add files to, for instance, this config.d folder for whatever repository you want to add to your machine. You have to put the public keys in the keys directory, and then you should be able to mount the repository. So you also have to do that for our repository, but you basically only have to do that once for our configuration region repository, which is called cvm-fs config.easyhpc.org. But if you look at the contents of that, that basically resembles the same structure as you will find in this etc cvm-fs. So there's just the etc folder, cvm-fs, and then the same kind of structure. And this just holds domain-specific configuration for the entire EASY project and all the different public keys that we use. So at the moment, there's not that much because we only have this pilot repository. So for instance, you will find only one key, only the one for the pilot repository. But the nice thing of having a structure like this is that clients only have to do the configuration once so that they have access to this configuration repository. And then all the extra configuration for all the real repositories that we have can be taken from this configuration repository, which means that if we want to add, let's say, 1 or 2 more repositories today, we just add the configuration for those new repositories to this cvm-fs config repository, and then clients will automatically get those files. So you don't have to change your clients or reconfigure the clients. They automatically just get all the new configuration and all the new public keys that you need to access those new repositories. So that makes it very trivial to change the configuration or add new repository without having to ask all the clients to reconfigure, which will be very annoying since you don't even know which clients you have. So you will need some, otherwise you will need some page which says, as of today, all clients should do this or make this change. But with a config repository, that's very trivial now. Also, the configuration of the configuration repository doesn't really change that often. So in principle, this is just something that you can do once, and then in principle, you don't have to change this quite often anymore. The only exception is if we add a Stratum 1, for instance, then clients may want to update their configuration so that the new Stratum 1 server is also included for this repository. Also for filling that repository with all the right configuration file, that's done by another playbook. So that's also in our repository here. Let's scroll up again. So there's a deploy cvm-fs config, which will basically generate all those configuration files for that repository on the fly and add them to the repository so that it's not manual work where you can easily make errors. So in order to configure the configure repository on a client machine, that's why you need this package, the cvm-fs config easy package, that will basically just configure your machine to use the configuration repository. And those are the packages that I just showed you. Then there is one quite annoying issue that we are running into at the moment, which is some kind of technical limitation in cvm-fs. That is that cvm-fs clients can only connect to one configuration repository at a time. So that means if your machine already uses some kind of configuration repository for another project, or for instance for the CERN projects themselves, then you cannot use our configuration package and configuration repository. There is some kind of workaround for that. We've also discussed that with the cvm-fs developers. So we can, for instance, add our configuration to wider packages that already exist. So CERN has a bunch of large configuration packages that includes lots of different projects and repositories. And we can try to merge our configuration with those packages so that if you install one of those wider configuration packages, that you automatically get the easy configuration as well. But if that's not possible for you to install, then there's well, basically just one other alternative, and that's that you don't really use our configuration repository, but that you set up the configuration yourself, which basically means that you have to take the contents of our configuration repository and store that locally on your machine. So add it to the etc cvm-fs folder on your local machine, which I think we can do with building another kind of package. So a package that will not use the configuration repository on your machine, but a package that will just deploy all the configuration files that we have, which has the disadvantage that those configuration files might change more often, especially if we want to add more repositories. You might have to update your package. But well, if there's no other way around it, then we have to look for such a solution. Then there's a client container that we provide. So instead of doing the cvm-fs mount yourself on your client machine, you can also use the client container that we store on Docker Hub. So there's an image on Docker Hub that you can easily pull in with Singularity. That's configured for you so that you can just run the container, and that will automatically mount our repositories in the container. So you can find it here on Docker Hub. The files that we use to build those containers can also be found in the file system layer repository in the containers folder. So there's at the moment 2 Docker files here, one to build a CentOS 7 ARM64 based container, and a similar one for x86-64. So it's based on CentOS, doesn't really matter since it's container, could also build one for Ubuntu if you want to. But we just built them for CentOS. And there's a script that will just build them and push them to Docker Hub. So if you're using Singularity, you can pull in that container from Docker Hub, and then you will have to use this --fuse mount option, which works in Singularity versions, I think 3.5 or newer. So then you can use that flag to basically instruct Singularity that once you're going to run the container, that it should mount the cvm-fs repositories. That's all documented on our documentation page for the pilot repository. And well, you can basically just copy paste a bunch of commands that we provide there, which will automatically do the initialization of the container for you. There's one kind of disadvantage with using Singularity. So it's nice for just playing around with our repository or testing it. But there's some disadvantages, which is why I think I would recommend, if you want to use this in production, that you shouldn't be using containers for this, but just use the native cvm-fs client, if possible. So one of the disadvantages is that each container instance will basically use its own cache, so you cannot share the caches between different Singularity instances, unless you set up the cache yourself first with a kind of alien cache. So there are workarounds, as Kenneth is just adding to the slides. But again, if you want to use this on a large cluster, for instance, in production, it's the easiest solution is definitely to use the native cvm-fs client if possible. So some other things about the file system layers, problems, goals, and to-dos. So one issue we have seen before is that cvm-fs often needs quite a lot of open files. Might even be the duplicate of the number of files that you actually access, because all the kind of tricks that it does with setting up a virtual file system where the files don't really exist yet until you access them, then it's going to pull in those files and store them in a cache. And then you basically access both the real file location and the file from the cache. So then you get twice the number of open files that you actually access. Which shouldn't really be an issue, but we've seen issues on systems where they have set the ulimit settings very low for the number of open files. And then you might run into some issues here if you're going to use it, especially if you're going to build software, for instance. We've seen it a number of times. A larger issue at the moment is that adding new software to our Stratum Zero is at the moment a kind of manual procedure, which is quite cumbersome. So since I administer the Stratum Zero server, basically I have to do this every now and then. For instance, Kenneth is doing lots of software builds, and then he ships them to me in a tarball, and I have to ingest them manually. So there is an easy command for doing that, to just ingest an entire tarball, which is quite easy, but still having a human in the loop, which has to do this every time. That's of course not the way we want it. So we want to automate this in some way. So we are thinking about some kind of workflow where we want to use GitHub Actions and GitHub Apps, which are kind of bots, which will start talking to each other. And ideally, we want to set it up in such a way that, for instance, let's say I have a EasyBuild recipe, so an easy config for adding a specific scientific software application that I want to add to a repository, that I can open a pull request somewhere on our GitHub repository and say, hey, I want to add this easy config for this particular software. Can this be included? That one of us in the project can have a look at that, can review the pull request and at some point approve it. And then this should somehow automatically fire off some virtual machines in the cloud, for instance, which will start building the software for different kind of architectures. And when that passes all the checks, at some point that it will be automatically ingested to our repository. So So we don't have anything for this yet, or not really. So we've looked a bit at Terraform and stuff like that, as Kenneth already mentioned, but we should really start thinking about this because we want to get rid of all those manual operations that we need now. So that's definitely something that we will be working on in the short future. Some other issues. So the cvm-fs repositories, that's all based on keys and whitelists of who is allowed to do stuff and access the repositories and add new files to the repositories. And in order for this to operate well, you have to re-sign a whitelist every few days. By default, that's once per 30 days. And for this, you need a master key to basically re-sign that whitelist, which is currently stored on our Stratum 0 server. And well, that might not be the safest solution. So if someone somehow breaks into the Stratum 0 server, he or she can steal the master key and start doing stuff to our repository. So a safer way to do it, which was recommended by the cvm-fs developers as well, is to use these YubiKey USB devices where you can basically store your master key on, and then you can connect that USB key to a specific machine, and then it can read out or not read out the master key, but it can use the master key on that USB device to re-sign the whitelist, basically. So then you need to have that USB key attached to your machine, but then you can run the appropriate commands to re-sign the cvm-fs whitelist, which is much safer. Then it's almost impossible to steal that master key. But the disadvantage is that then someone in the project needs to have this key, and well, preferably more than just one person. So a few persons should have a YubiKey with the master key, and then these people should re-sign the whitelist every now and then. If you use this, then also the period for signing the whitelist goes down to 7 days by default. So then you have to do this once per week, basically, which, well, we should think about how we want to do that. It's still not the most convenient way to do it, I would guess, since, well, you shouldn't forget about it, and it has to be done every week, and it's still some kind of manual procedure. But we should think about it, especially when we go into production at some point. We also need a lot more documentation for the file system layer. So as you saw, there's quite a lot of stuff in the README now, but we should start migrating this to proper documentation and document different kind of use cases. So we now basically only explain the Singularity container, how to use that, but we should start documenting how to install the native client, how to set up the alien cache for special kind of systems. For instance, if you have compute nodes in your cluster which don't have a local disk or don't have internet access, you should set up documentation for this and explain how you can then still use cvm-fs. We also want to do some more monitoring and get some better overview of user statistics, for instance, and well, just show an entire overview of the entire infrastructure that we have for our cvm-fs setup. And well, Kenneth already mentioned that there's some interest from cloud providers like AWS and Azure to sponsor us. So maybe you should also start setting up Stratum 1 servers in the cloud instead of locally, or do both, and maybe even move the Stratum 0 into the cloud. So that's all I wanted to tell about the file system layer. So I'll have a look if there's anything in the chat or other kind of questions.
Yeah, there's a couple of questions in the HackMD, but we're trying to answer those as you talk. There's maybe one from Alan that says, I saw a bit of a load from cvm-fs when populating the cache. I think that's the alien cache. Are there any recommendations for a cache size to control this?
So you saw load on the client, I assume.
Yeah,
yes, this
not
is
the alien
client.
cache, actually, just the cache in general.
Okay, yeah.
So I was actually doing this in Magic Castle, so it just uses a normal cache, but it was quite a heavy load actually, when it was doing the initial population. Yeah. And I was wondering if you had a small cache size, then you might be thrashing that a little bit.
Yeah, I can imagine that you will reduce the load, at least for the initial access, but then you might spread it out over a longer period because you have to wipe stuff from the cache more often. While with the larger cache, you we'll see an initial spike probably indeed if you want to access some first applications that you haven't used before. But then it will all be stored in the cache if the cache is large enough. So then the next time I assume that the load should be much lower than that. So it's probably a bit of trying out what's the best option for you.
And also, I guess the location of the cache matters a lot. It has to be on a fast file system.
Yeah, definitely. Yeah.
So don't use NFS or something like this. Use at least local disk, preferably SSD. And if you have enough memory, just park it in DevShmem, in RAM disk.
And maybe adding a local squid proxy between the Stratum and your machine might help, especially if you want to make the caches smaller on the local machines. Then still you have a larger cache nearby with your squid proxy. So it's a bit of a hard question to give the right answer, I would say, but
and a proxy can also avoid that you're actually pulling things down from the other side of the world. So you have them, or they only do that once at least.
Yeah.
Yeah, I guess my point is that it's something that people should be aware of, right? And that we probably need to document a little bit about what people should look at in this case.
Yeah.
I think this is covered pretty well, I think, in the cernvm-fs documentation. But we can point to that. Yeah.
Is there anything else?
There's Bartosz also had a question. He has his hand raised. So.
Yeah. So you discussed a little bit the security of Stratum 0 and Stratum 1. Where Stratum 1 is read-only and Stratum 0 clearly uses some key-based authentication to write into the software. But what about the client side? So when you download this configuration file, imagine your GitHub account is taken over even just for a short while. And then somebody modifies this client configuration. And then all the clients pull that new config file, and suddenly all clients point to a hostile Stratum. Is there any plan on preventing this from happening?
So you mean if files in the configuration repository itself get somehow?
So the cernvm-fs config file that you showed at the very beginning on the client side.
Yeah.
I don't remember which slide it was.
So yeah, if someone gets access to basically this this repository and can change these files.
Yes.
Let me think about that one. What's the worst that can happen?
Well, if they have access to the cernvm-fs repository, regardless, you're in trouble.
Yeah, that's already an issue indeed. But if somehow indeed they would change the GitHub and we have set up something in such a way that it will automatically deploy this to GitHub, then maybe then they don't have direct access to the repository, but still, for instance, this could be changed, if that's what you mean.
Yes, that's exactly what I mean. So you just point this to a hostile repository.
Yeah, I'm not sure if that's completely possible, because this is, as the directory name here suggests, it's domain specific. So it's only stuff for this domain that you can change, but you could probably add your own Stratum 1 server, which will still have our repository, but then start changing files over there. But that doesn't really work, because cernvm-fs does have lots of features built in to ensure that you get the right data based on checksums and catalogs, for instance. So if you access a file in our repository, basically what it will do, it will look up in a catalog, which is just a SQLite database, which actual compressed version of that file it should pull in from the Stratum 1 servers. And that also has a checksum. So before actually executing that piece of code in that file, it will verify the checksum downloaded and make sure that it corresponds to the checksum in the catalog. So I don't think you can do that very easily. Now, I'm not a security expert, so I might miss something here, but yeah, we can definitely ask the cernvm-fs developers, but I know that there are lots of features built into cernvm-fs to guarantee that you get the right data, and it will be hard to mess around with that.
Yeah, so
of course you can.
With respect to the automation, we indeed have to be careful and certainly have security in mind. So we want to make things automatic, but first of all, we should be notified if things are changed, and preferably multiple people keep an eye on that. Monitoring may help there as well, and just try to avoid humans being involved too much, but enough that you at least are still actively keeping an eye on things, and that at the very least you notice when something malicious has happened and you notice it quickly.
Also on GitHub, we've set it up at the moment in such a way that even I or Kenneth cannot directly write to the master branch, if I'm correct.
Yeah.
So if I want to change the configuration files on GitHub for the repositories, I really have to make a pull request. So, and then I can probably merge it myself, but then still people get notified that a merge request was merged. And I think they will spot immediately that it's my own pull request and that something weird happened.
Of course, if they have access to your GitHub account, they could change that setting and just push straight to master.
Yeah, that's true. Will you get notified about that? Probably.
No, if a commit just is pushed to the repository, you don't get a notification. But if somebody pulls or you check history, depending on how good they are, they may clean up after themselves, and there's lots of nasty things they can do.
Yeah. But we can definitely also think about procedures for not automatically deploying new configuration files to the repository before someone really approves that. And of course, if my
for things like this, I wouldn't make it fully automatic actually, because that especially the configuration repository, that's pretty infrequent. That's only when changing the configuration or adding a stratum 1, we won't be doing that every day. But the deployment of software in the software layer, that should really be as automatic as possible, again with security in mind. So locking it down to certain trusted people or SSH keys and refreshing them regularly, things like this.
Thanks.
So I don't think we have perfect answers to that. That's something we'll need to discover a bit, but it's pretty clear that if everybody starts mounting this on their site, you have a pretty big attack surface. So it may be, it's actually going to be very important to make sure things are secure and auditable, so we know what's going on. And there's a cernvm-fs can use certificates to make sure you're not subject to a man-in-the-middle attack. Yeah, it has internal built-in stuff, so a client will actually verify checksums that it gets from the stratum 1 or stratum 0, so that it won't be easy to just inject something in the middle and serve you a different binary. But it does have lots of protections for that. This is used on the biggest grid and HPC sites around the world, so it's not a toy project in that aspect.
Yeah, I'm not worried about the once you are connected to the right cernvm-fs. I'm not worried anymore, but I'm kind of worried about this configuration file where you would just point it to something else and potentially you wouldn't even notice.
Yeah, so that's certainly something we have to make sure we keep a good eye on, and especially there, not go too automated. And of course, the people who have access to stratum 0 are locked down. And maybe, if this is a big security concern, maybe that step will keep that manually, where somebody who has access to stratum 0 just does a manual pull of the GitHub repo, maybe the triple checks what's being updated before actually deploying it live. So the real automation part is really on the software layer, because there things will be added very frequently, and keeping the human in the loop there, that won't work. Okay, Bob, I think we should continue because it's 25 past 11.
Yeah. I was just quickly going through the questions on the document.
Yeah,
I see that you already answered most of them.
Yeah, Alan and me will keep working on trying to answer the questions that are posted there. We'll try to keep some time for questions at the end as well.
Yeah, then I'll quickly continue with the compatibility layer. So that's the kind of operating system layer in between that we use to provide all the system libraries like glibc. So everything except the kernel and the drivers and stuff like that. Well, Kenneth already explained most of this, so we use Gentoo prefix to do an installation. I can quickly show you how that looks in practice. So we have a full installation, everything that we want to install, we install that to our repository in a folder called compat for the compatibility layer. We currently only have something for Linux. We are working on a compatibility layer for Mac OS as well. Well, let's check out the one for x86-64. And then this is what you will have there. So it's just a kind of root Linux file system over here with bin, lib, etc. And then some tools and libraries in there. So we can configure what we want to install and what we need, but we try to keep it very minimal. So we do one per family of CPUs, since the things in here don't need to be heavily optimized. So we just have one folder for all x86-64 processors and one for all the different ARM64 processors, etc. So we are working on a separate macOS version as well. Well, I already mentioned this. And we try to not update this too frequently. So of course, when there's a security issue with, for instance, glibc, we will try to update this as soon as possible. And Gentoo also provides mechanisms to monitor for security incidents or issues with the packages that you have installed. But we will not, for instance, update this every day with just the latest and greatest versions of all software to make sure that our software keeps working. Well, already did this quickly, but this shows again how the structure looked like. So in the bin folders, you just have all the standard Linux tools that you expect to find in the bin folders. So I can quickly show you, for instance, the lib64 folder. You don't have that many libraries in here. So just a bunch of things that we need. And same for the user lib64. So there's quite a few, but not too many. So we try to keep this limited. So how does this work? Again, we use Ansible for the installation. So we have a playbook in our compatibility layer. Quickly show that one. So this is the compatibility layer repository. And the main installation file that you will need is in the Ansible playbooks folder. There's an install.yaml file over here, which will make use of the compatibility layer role that we have. That has all the individual tasks that are going to be run and configuration files for that role. And this is just the main file, which will run that role basically. So here it runs the entire role. So in here you will find all the necessary tasks, for instance. So we have a bunch of different steps that we want to run in this role, which is, for instance, install the Gentoo prefix installation. That's the most time-consuming part. That might take us several hours to complete, because it has to build that whole Linux installation from source. We have a task that basically adds our overlay, which is our repository with Gentoo packages to the installation when it's done. So then we'll add the overlay. It will install some packages from our overlay. For instance, lmod is a package inside our overlay, because by default it was not included in the Gentoo repository. And some other ones to just fix a few issues or configure the prefix installation. So we'll install prefix, add the overlay, install the packages, where we have sets for each specific architecture, because sometimes one package doesn't work on a specific architecture. For instance, for special interconnects, sometimes these don't work on ARM64 systems and only on x86-64. So then we only install it for that particular architecture. And the configuration that I mentioned, one of the things that we, for instance, do is make some symlinks to files on the host machines. For instance, LDAP libraries, we link those to the host if they are available on the host. And that means that if you have LDAP on the host, for instance, on a cluster, then also inside the prefix installation, it will find those LDAP libraries, and automatically LDAP will then work inside the prefix installation, which means also the software in the software layer will be able to look up your user ID. To install Gentoo prefix, you have to run a bootstrap script, which we've taken from the Gentoo project. We had to make a few small customizations to that, but basically we can just take it as it is and run it. but we keep our own copy with those small changes. And we also make or keep our own copy of the prefix snapshots. They make one every day, and we just download the one that we used for our specific installation and store that somewhere locally, so that we can always try to reproduce the installation if necessary. And that snapshot, that's not a full installation, but that's just basically the recipes that it used to build all the components inside the prefix installation. So that you can be sure if you use that snapshots that you can reinstall the same versions of all the different packages. Also for this repository, we have a nice GitHub action, which runs every time someone pushes a new change to the repository. And what it will do, it will take a container from Docker Hub, which has a prefix installation in it, because building the prefix, as I mentioned, that takes several hours, so you don't want to do that for each commit. Also, there's a limitation on the runtime for a GitHub action, which is, I think, a few hours. So that doesn't fit. But we just take the latest version of the prefix container on Docker Hub, and then run our playbook inside that container, so that it skips basically the prefix installation, but at least does all the other steps in that container, and make sure that adding our overlay and installing our packages, that all still works. Well, we have to run that playbook multiple times. So as I mentioned, once for each CPU family. So at the moment, we're building for only x86 64 and ARM 64. So we basically have to run this playbook on 2 different machines. This is our link to the Gen 2 overlay. That's basically just a repository on GitHub with customized EasyBuild files. EasyBuild files are what Gen 2 uses to basically provide recipes to install packages. So that's another repository here on our GitHub page. And well, it's all in different kind of categories that Gen 2 uses. So for instance, there's a app admin category that Gen 2 uses, and we've added the lmod directory in our overlay, which just has a bunch of lmod installation files. So that's just how lmod should be installed in the Gen 2 system, and defines the version and the source files, for instance, things like that. There's also some specific configuration files for Gen 2 in here. So Portage is the package manager of Gen 2. That's what is being used to install all these packages. And there's some specific configuration files here in our Gen 2 overlay as well that we use on our prefix installations. For instance, the set definitions that we use. So this is just the main set of packages that we install for each architecture. So for instance, we install lmod, we install some editors and some fonts and other stuff, archpack as well. And as I mentioned, we have a specific set for each architecture. So for instance, for x86 64, there's some libraries here, for instance, to make InfiniBand work. And there's also one for ARM with some other kind of packages, because not all those packages from x86 64 work on ARM as well. So let's go back here, and I think I've covered all of this. So the current status, so what we have on GitHub right now that works pretty well. So every now and then we want to make a new pilot version. We need to update a few things. For instance, we want to sync in the latest changes to the Bootstrap script from the upstream changes in the Gen 2 repository. Of course, we want to try to use the latest snapshot then and store that snapshot on our servers. And well, sometimes there are some differences in the installation, which is okay because, well, some combinations just don't work with special interconnects on weird architectures, for instance. So it's fine that the installations are different. The primary contact for this layer is Peter. I think he's here as well. So if you have questions about the compatibility layer, ask him, or just ask in the Slack channel that we have for the compatibility layer. Some goals of and things that we want to do or work on in the coming time. So also here we want to add more automation. We don't have to run lots of stuff here. So basically run that playbook several times for the different CPU families. But also that we want to try and automate so that you can just fire off something which will automatically, for instance, to spin up a machine somewhere in the cloud and then run that playbook there. So our Gen 2 overlay, that's based on a fork of Compute Canada, as you we'll see here on our GitHub page. That's just because we started with whatever they had, but in the end we didn't really use their files. For instance, their configuration files are very, very different from the ones that we have. So probably we should defork that repository and set up our own version with only the stuff that we added and need. I'm currently working on power support for the compatibility layer as well, so that we can start offering software for power CPUs. That's still work in progress. I'm getting quite a lot of help from the Gen 2 developers, but there are some issues. It doesn't seem to work very well. So I hope to finish that soon. And I already mentioned Gen 2 has a nice system to scan for security vulnerabilities. So if there's a known issue with one of the packages that we have installed, you can get warnings by using a tool, which I run every now and then manually. But of course, we need to set up something for this as well, so that we somehow run this on a specific system and get alerts if something is wrong and if we should update something, so that we can fix that as soon as possible. Okay, that's it for the compatibility layer. So are there any questions about this layer?
Yeah, there's one question here about the lifetime of the compatibility layer. So basically, how long will we use it? How long will we keep it? What happens when it gets a major upgrade? So I think the answer is there. We haven't figured that out yet.
Yeah, that's what I would say as well.
And in some sense, we have the idea of rebuilding the compatibility layer once or maybe twice a year, or maybe only when there's an actual need for it. So as long as we don't need the newer glibc version, for example, we probably won't, because rebuilding the compatibility layer also means starting from scratch in the software layer. So redoing all those installations. That's not a huge problem since we have EasyBuild and everything is really automated there, at least individual installations. But changing things in the compatibility layer may affect the installations in the software layer as well, of course, in terms of suddenly one installation no longer working because something has changed in the compatibility layer. So it's not something we want to do very frequently unless we have to. What we will do, of course, is security updates in the compatibility layer. As Bob mentioned, we're trying to keep an eye on the security alerts that are being sent by Gen 2. But hopefully those won't warrant a rebuild of the software layer. And that also ties in a bit to the testing that we haven't really actively worked on yet. So we want to make sure we have a test suite that says, okay, say if we update glibc to a newer minor release because of some security related issue, we do a glibc update. Does that have any effect on the software layer? So do the installations still work? Do they still perform as expected? And if not, how bad is the performance degradation? So you can imagine with things like what's it called, Heartbleed and all these things, there was performance impact as well. So we need to take that into account too. So right now, we actually rebuild the software layer for every revision. So the compatibility layer for every revision. So the 2020.10 pilot version and the 2020.12 pilot version have a different compatibility layer, but that's just also because we want to experiment and make changes there. So it's definitely not production ready yet. And what we will end up in the future is not decided yet. So I hope that answers the question. Also, in terms of how long will old compatibility layers be kept, I would say as long as disk space allows it, we will keep them. But maybe at some point we will actively discourage people from using an old compatibility layer installation because, for example, there are known security issues that we don't plan to fix there, or we know some things are broken and are impossible to fix without affecting software installations on top. So yeah, we're probably still experimenting a bit too much there to have a clear and fixed policy for that. I hope that answers the question a bit. So let's switch again, Bob.
Yeah.
You'll have to give me screen share permissions, it seems. I'm no longer host, that's why.
Host and are you in my screen? Yeah. I cannot make you a host, but why not?
Maybe Terry can.
I dominated it. You're a host now, Kenneth.
It still doesn't allow me to screen share.
Okay, try now.
Yeah, now you are.
Yeah, okay. All right, then software layer. So we'll try to wrap up in time. Not sure if that's going to be possible. So what are we doing in the software layer? So we're combining EasyBuild, LMOD, and Archspec to, EasyBuild to do the installations, LMOD to consume the installations via module files, and Archspec is used to do the detection of which CPU is used in the host and which part of the software stack of a software layer that has to be picked up. So the installations in here are specific to CPU microarchitecture. So we have the separate one for Haswell, for Skylake, for AMD Rome, for the ARM Graviton 2. So those are basically duplicate installations, but properly optimized for these architectures. All the software is built on top of the compatibility layer. So as much as we can avoid it, we don't use anything from the host OS. When we do these installations, we use a singularity container to have full control over the build environment. So we set up a pretty minimal, I think it's CentOS 7, or maybe it's I actually think it's Debian. Use Debian and a container image that has almost nothing. It basically only has cvm-fs and the Fuse overlay tool. And it doesn't see anything from the host operating system on the build node. So we have full control over the build environment. The modules are also included in the software layer for now only in Lua syntax. So you have to use LMOD to consume them, but we'll probably add Tickle syntax modules as well. And these can live next to each other without causing problems for LMOD or Tickle only environment modules tools. The way the software is installed here is scripted. So we have a script that we run. We don't do any manual EasyBuild commands, but we don't think this is good enough. We want to automate this further, and especially the procedure of actually pushing things into the repository, so ingesting them into cvm-fs. That part definitely has to be automated as well. The build container is relatively similar to the client container, so it has cvm-fs inside. You don't need cvm-fs on the build node in the host OS. And one difference here is that we also add this Fuse overlay FS tool. So we basically mount the existing cvm-fs repository and we add a writable overlay on top, which is where we do the installations in. And then whatever is added in this writable overlay, this is where we take the tarball of the installations that were added. We push this to Stratum 0 where it is ingested into the repository. The client container or this build container is also scripted. So there's Docker files and a build script included in the software layer repository, if you want to take a look at that. We've run into some weird issues with the Singularity and Fuse overlay FS combination. And there's a ticket for that in the Fuse overlay project. There's no solution for this yet, except that if we use an old version of Fuse overlay FS, it actually does work. And we haven't seen problems with the old version. So it seems to work, it's good enough. It lives in the build container. You don't have to install this in the OS. So it's not a huge problem, but of course, yeah, it would be good if we fix this somehow. And I guess we need to talk to the Singularity guys or the Fuse overlay FS people again to try and sort this out. They had some issues with reproducing the problem, for example. Yeah, again, it's a minimal container, so we don't pick up anything from the OS, and Fuse overlay FS creates the writable overlay. And yeah, the stuff we install ends up in that writable overlay, and then we grab it from there to add it to the cvm-fs repository on Stratum 0. The build script, which you can find here, it's a pretty ugly bash script, which just runs EasyBuild a couple of times to install different software that we include in the pilot repository. It starts with the toolchain first, and then I think GROMACS on top, and then TensorFlow. So we do things step by step, sort of, to have a good view on what is failing. But we want to clean this up. We recently added support for what's called easy stack files. I should say experimental support for easy stack files in EasyBuild, which is a more clean way to specify what a software stack, what should be included in the software stack, and you just give an easy stack file to EasyBuild and installs everything that's listed in there. So we want to clean up this build script so it only runs EasyBuild once, and it gets an easy stack file that lists everything that should be installed. The easy stack files implementation right now is not capable enough yet to replace the build script, so that's being worked on. The build script is CPU microarchitecture agnostic, so we run the exact same script on a Haswell or on an ARM node, and it just works well. It configures EasyBuild to install in the right location and all of that. So there's nothing manual you have to do other than just running the script in the build container. And then, yeah, the overlay directory is then tarred up and sent to the Stratum Zero for ingestion. So that's a manual step right now. That's where we still have two humans involved. The person that did the build has to tar things up and send it to Stratum Zero, and then Bob has to ingest it on Stratum Zero. So we want to get rid of that. We want to automate that part. The initialization script is also included in the software layer, as well as in the actual Easy repository. So you can source the script to set up your environment to use the software provided by Easy. The first thing this will do is use Archspec to detect what kind of host CPU you have, and then to find the best match compared to what's included in the Easy repository. So if we have installations currently for x86 Haswell, or x86 Intel Haswell, and x86 Intel Skylake. If you're on a Broadwell, Archspec will tell you, okay, there's nothing for Broadwell, but I see Haswell is there, and that's the best match for you. That will still work and give you the best possible performance out of the options that are available. So that's fully automated. You don't have to tell the init script what you're on. Archspec can do that for us and give us the best match. And the init script is now split up a bit into separate scripts. Actually, the init bash one is the one you source when you just want to use the Easy repository. But we also have a separate one for Magic Castle, which is a cloud environment or a cluster environment in the cloud, where things need to be done a little bit differently. And this script sets up the environment variables. It's sourced by the bash and the Magic Castle script. And this Python script is the Archspec part, which figures out which part of the stack to use. And there's a README file as well that has some details on what each of these scripts do. Then the status in the software layer, in the pilot repository, we include a handful of applications that we think are enough to show that we can do what we have in mind. So Bioconductor and R, GROMACS, OpenFOAM, and TensorFlow. We have example scripts for these in the Easy demo repository, where you can just go to the right subdirectory and run the script once the Easy environment is set up. So it will load the GROMACS module, do a small GROMACS run, so you can see things are actually working. For some of these, we had to push upstream fixes to either the software itself or some of the dependencies. A lot of that has been done for ARM and Bioconductor and R packages, for example, and also for Power, especially for TensorFlow. Some patches are included in EasyBuild or have been pushed upstream to fix problems that we saw there. That's actually separate from Easy. Those would have to be done anyway. They're not really specific to the way we do things in the Easy project. For some part, the installations are built mostly in AWS currently. So whatever for Graviton 2, for Haswell and Skylake, we could also do it there. Up until now, they've actually mostly been done on the clusters we have in Ghent. So we just run the script on a worker node, let it run overnight, and with these installations in less than 24 hours, you have everything built. So it's not a huge issue for now to only use a single build node for that. But also there, we want to make some changes. And when building in the cloud, you have to be a little bit careful, because if you start a cloud instance, you're not always in full control over whether you land on a Haswell or a Skylake node, for example. So depending on the type of instance you start, you may or may not have control over what you actually get. And that's, of course, a problem, or something that we at least have to be very careful with. We will also like to look into GPU-capable installations, especially of TensorFlow and GROMACS, which have good GPU support. One of the things we first need to look into there is whether we are actually allowed to redistribute a CUDA installation. And it seems like we can, but we have to strip it down to only the runtime parts. So the runtime CUDA library, you're allowed to redistribute. You're not allowed to redistribute the NVCC compiler, for example, and you get both when you install the CUDA toolkit. So we have to strip down the installation we get by default in EasyBuild before we can actually include it into the Easy repository. And maybe we'll have to reach out to NVIDIA there and make sure we're not working ourselves into trouble. And yeah, I'm the primary contact for the software layer since this involves lots of EasyBuild stuff. I've been very active in this part. What does this look like? I can actually show it interactively. That's maybe a bit better. So this is the pilot repository. Let's just look at the latest version, 2020.12 we have. Compat layer, I won't look into, that's been covered. This is the init script. So this init bash script is the one you source. And I can show it here. This is a VM cluster with Intel Haswell CPUs, and the init script just detects that thanks to Archspec. So it detects that it's on Haswell, and then it will use the right path in the software layer to use the Haswell installations. And then the software subdirectory, this is where the software layer lives. So this has separate installations for ARM and x86. In x86, we have AMD and Intel separately, and a generic software stack. So this has software modules and software directly under. If you look into the Intel one, you'll see again split up for Haswell and Skylake. And for AMD, we have the Zen 2 or the Rome installations. And very similar for the ARM 64-bit, we have a generic and then a Graviton 2 and a Thunder X2. So here we don't split up between vendors. That makes a little bit less sense for ARM, because almost all the different CPUs you have will have a different vendor. But for Intel and AMD, we wanted to make this distinction. Maybe we will change this if we think these names like Haswell and Skylake are good enough to discriminate between AMD and Intel. We may kick out these subdirectories. And then when you look into a specific installation, you'll see a modules and a software subdirectory. So people who know EasyBuild know what's in there. For the modules, you have the actual module files. This is just a subset of the modules, of course, but for each application and for the toolchain and our core compiler, there will be modules available, and exactly the same in the software subdirectory. You'll have corresponding installations. And for particular software like OpenFOAM or TensorFlow, you have again subdirectories in there for the version. And of course, corresponding module files that are in this modules all directory. So this is not too surprising. It's pretty standard EasyBuild. For testing in the software layer, so this is something we've mostly had discussions about up until now. There's been some hands-on work, mostly by Kaspar, to try and figure out the best way of doing this. We want to use Reframe here. That's the software regression tool that's implemented at CSCS, and use Reframe for the different types of tests we want to run. So something we call smoke tests, which are very quick tests that run in a matter of seconds, and which we can probably use in a CI environment like GitHub Actions to make sure the software is actually working. And then, yeah, larger tests running from a couple of minutes to maybe half an hour or an hour to even large multi-node runs, and yeah, everything in between. We hope to eventually have in the test part of the Easy project, and also scaling runs. So if you have multiple nodes, how well does the software scale? Is it properly using the network? Things like this. So right now we haven't really done anything complete, let's say, with Reframe, or we're still figuring out the best way of doing that. We want to avoid that we implement the tests in such a way that every site has to change them according to their local hardware. So in terms of how many cores you have per node and things like that. So we want to have a good way of dealing with that and separate the site specific and the common things, which is, it's not really a problem in Reframe, but they haven't done a lot of work yet to avoid having hard-coded stuff in tests. So we're figuring out the best way forward. There have been lots of testing, mostly manual, by several people in the EASY project. For example, in Jülich, where Alan has tested lots of stuff with GROMACS and run multi-node GROMACS runs that perform really well, that show to properly use the network and the optimized MPI installation we have in the EASY repository. I'll continue to the end of the presentation, but if there are questions on the software layer, I'm happy to answer them at the end. The documentation part, so that's again is a separate repository under the EASY organization in GitHub. So this is what is available through easy.github.io/docs, which includes how to access the pilot repository through Singularity. This is written, the documentation is written in Markdown files, and we use the mkdocs tool to render them with a particular theme. And there's a small makefile available if you want to locally build the documentation. It's very easy to do. You can just run make, or you can run make test to make sure there's no broken references in the documentation. Or you can even run make preview, which will start a small web server that has the rendered version of the documentation. So it's very easy to work on the documentation and see how it will look like in the end. So you don't have to make any guesses by editing Markdown files. You can actually see what things will look like. Whenever an update to the documentation is pushed into the repository, the corresponding website here /docs is also refreshed automatically. So this is done through GitHub Actions, which basically runs make, or actually runs make test first to make sure nothing is broken. If it's happy with that, it does a make deploy, which pushes an update of the actual documentation. That's at least that part is fully automated already. And here Robert is sort of responsible for keeping an eye on the documentation and making sure if we get any pull requests there, they get handled. Then on GitHub, lots of this has been covered already. So we have a central place where we have all the code, all the documentation, all the open issues, the things we want to work on. We have a project dashboard where we try to get organized a little bit. So all this is done on the EASY GitHub repository. We have separate repositories per layer. So file system layer, compatibility layer, software layer. We have this Gen2 overlay fork from Compute Canada. Like Bob mentioned, we want to get rid of this because it doesn't make a whole lot of sense that it's forked from Compute Canada, since we're not pushing back anything there, and we've made enough changes that it's really a separate repository by itself. Maybe it makes sense to just collapse this into the compat layer repo, just in the subdirectory or something. So we have everything from the compatibility layer in a single place. Additional repositories for documentation. We have a meetings repository, which is where we really only use the wiki to take notes for meetings, which is also where we will copy paste the HackMD notes and the Q&A there, post it on the wiki there so it stays there, and a separate repo for demo scripts. And ideally, all the to-dos we have in mind, so things we need to fix or change or need to look into, have a corresponding open issue in GitHub. That's probably not the case today. So I'm pretty sure there's things mentioned in the presentation here that we don't have a corresponding issue for yet, but we should. So if you notice anything missing that you care about, feel free to open an issue so we can keep proper track of what we're doing there and what needs to be done. And we also have this dashboard, this project dashboard, for example, for the 2020.12 pilot update. We had this to keep track of what still needs to be done. Some of the things are open here, which we probably actually did already, but maybe they're still open because we want to automate that part of the repository. And there's currently no other projects here, but we're thinking about adding a project, a themed project like security or automation, where we can collect issues that are related to that aspect. So we want to get a bit more organized there, so people who care about a particular aspect can just focus on that project in in GitHub. The Git workflow, that's maybe also important to mention. So all changes we make to the repositories are done by pull requests. So nobody pushes directly to one of the easy repositories. That's actually blocked, so you cannot push directly to the master branch. All the pull requests are reviewed and merged by somebody other than the author. So even if you open a pull request, you're not, I think it's actually blocked. You're not allowed to merge the pull request yourself. Somebody else has to take a look at it. So we have this 2 pairs of eyes policy. Never merge your own pull request. Let somebody else handle it. And either you're just patient and you wait until somebody picks it up, or you mention it on Slack or ask somebody specific to take a look at it. And there's only a few people per repository that have merge permissions currently. So basically the people who were involved with the start of the project, but we can consider extending that. If there's people who get very active in the project, we can look into giving them merge permissions as well. And last year, we had a Git training for people who are not very familiar with Git or GitHub, which was also recorded. So if you're new to this, take a look at that. And that's probably useful to get you up to speed a little bit. And then in terms of resources we have available for the project. So in AWS, Amazon has given us quite a bit of sponsorship. A large amount of sponsored credits have been made available to us recently through the University of Groningen. So they are the receiver for, and they manage the credits, but basically anyone who's active in the project can get access to the credits for stuff related to the project, of course. So we haven't really started using these yet, but we're thinking about installing Stratum 1 servers in AWS Cloud, probably multiple ones in different regions, in the US, in Europe, maybe also in Asia. And we can use the resources there for build nodes, for building the compatibility layer, building the software layer, also testing things, of course, with different operating systems, for example. And EC2 supports both Linux and Mac OS, so it's very attractive for us. It also supports instances with AMD, Intel, and even ARM processors, so their own Graviton 2 processors. So it gives a pretty wide range of things that we can play around with there. Likewise, Microsoft Azure is looking into sponsorship. They're sponsoring the cernvm-fs tutorial that we're doing at the EasyBuild user meeting next week. And they're looking into more structural sponsoring, but we're figuring out the red tape. So where the sponsorship could land and how that could be distributed among the partners in the project. So that's not fully clear yet, but it's a work in progress. And then the OZU open source lab, this is a service where you can just ask for VMs for open source related work. And through this, we got Power 9 instances via OpenStack, I think, Bob, where we can fire up instances as we need them for testing. So Bob has been playing there with the compatibility layer, for example, and trying to get Gentoo prefix to work. And of course, it's also individual resources like Terrier's Mac Mini, which has the new M1 ARM processor, or the clusters in Ghent, which I have been using for building software for the pilot repository and so on. And of course, anyone can test on their own systems to see if things are working or to contribute back to the project. And then to wrap up with, before we do a bit more questions, the organization in the project is a bit, well, chaotic is maybe not the right word, but let's say informal. So there's no, since it's not a funded project, there's no real management of the project. So people just work on it when they have time for it and work on the aspects they care about most. We do have monthly update meetings, which I think most of you have already attended. So every first Thursday of the month at 2 p.m. European time, we have a monthly update meeting, which takes about 2 hours, and we give an overview of what has happened in the last month, what people have been working on, what has changed, and what we would like to work on in the coming weeks. In between the monthly update meetings, we also have more focused meetings with a limited amount of people who, for example, look into reframe and what we want to do there, how we can do it. And sometimes we pull in people from outside the project. For example, the reframe developers have joined us, or we've had discussions with Compute Canada or with the cernvm-fs developers. So we try to reach out to the other communities as well and get answers to the questions that we have. We try to do a monthly update of the pilot repository. We didn't do one in November, but we do have one for December. And if we want to make some changes, we should get started on the January version soon. Sometimes we just skip a month because we've been focused on other stuff. For example, setting up this meeting or preparing presentations. So there's lots of presentations coming up on EASY in the coming weeks. So that has been where we spend most of the time currently. The Slack channel is pretty active as well. So we have focus channels in there separate for compatibility layer or EasyBuild or reframe. So people pop in and out of there if they have any questions or problems. And everybody who has signed up for Slack is also on the EASY mailing list. So if you want to contact everybody involved in the project, you can send an email there. That's all we have in terms of slides. I think we can walk through questions a bit if there's any more questions before we wrap it up. We're going over time a little bit. So
there was just one question in the document about comparison with other tools like Spec, but Ellen already answered it, I think.
Yeah, so the main reason I guess we're using EasyBuild in the software layer is because most sites that were involved with the start of the project were also already using EasyBuild. So it was a natural fit, I would say. I was invited into the project because of EasyBuild, because they wanted to see if that makes sense and if they could get some help from us with that. But actually, there's nothing really specific to EasyBuild in the Easy project. We could just as well use Spec to install software in the software layer or any other tool. Related to Spec, the better question is maybe how Easy compares with the is it Exascale for science? I always forget the right name. The E4S project, which is a bit similar to Easy in some sense, but again very different. Sort of similar to how EasyBuild and Spec are different. So in the E4S project, they're more looking at providing pre-built packages for software, where in the Easy project we give you a repository where everything is just in place. You source the script and you're ready to go. So there's lots of details there, and if people are up for discussing that further, I suggest to reach out to Slack via Slack and get some more info there. So any other questions before we wrap it up? I see no hands raised or no questions in the chat or in the HackMD, so I think we're ready to wrap up. If there's any more questions popping up, so please join the Slack channel. If you go to the EASY website, so easyhpc.org, there's a join link there with a small form. If you fill out the form, we will add you to the mailing list in the Slack channel. Yeah, Christian?
Do you mind if I plug a little, like an shameless plug here, that if you want to try this out, then just reach out to me as well. If you want to try this out, we can set up some workshop or something, or help you give some credits if need be, and then off you go. So feel free to reach out.
So Christian is from AWS. He's been helpful with providing us credits for quite a lot of credits that we can use for the project. So, okay, if there's no more questions, then I guess we can wrap up here. I hope this was useful. The recording will be available shortly this afternoon, so you can wind back and check some of the things we've been discussing. And if there's any questions that pop up, don't hesitate to reach out, Slack, email, or whatever way you see fit. Thanks, everyone.
Thank you.
Thanks, Kenneth.
Thank you.